This is the first section of chapter 9, which is about reducible differential equations. And this section is, we're going to be concentrating on first order differential equations. Now, basically, a reducible differential equation is an equation we can make easier by substitution. Okay, so we can use substitution to make a differential equation easier to solve. Now, you would have learned in Pure 2 how you can actually do integration by substitution. I'll put a link to that. Integration by substitution. This is a similar thing, but you'll see these substitutions look slightly different. And to do these substitutions, we are going to need to be able to do implicit differentiation and be comfortable with doing that. So here's an example of what we might have as a substitution. So let's say I had y equals, let's say, xw, and both x and w are variables. Okay, so let's say this w here is not a constant, it's a variable. So if I find dy dx, I'm actually going to be using the product rule because I've got, as I said, two variables here. So if I use the product rule and I call this part u and this part v, then uv dash will be x. Now, when I differentiate this with respect to x, w, you can write it like this. Or think of it like this. I'm differentiating a w as if it were an x. I've thus differentiated w with respect to x. So it'd be x dw dx. So I've just differentiated that as if it were an x term. So this is our implicit differentiation plus. So here's my u, here's my v dash. So the next bit is going to be vu dash. So v is just going to be w. And then, well, if I differentiate x with respect to x, it's just 1, isn't it? So basically w times 1, I don't need to put the w times 1, but it's just to show you how this all works. So this would be my v here, and this would be my w. So I'm using the product rule here to differentiate this. Now, whenever we do any type of substitution to make something easier, we're going to substitute back at the end. So substitute back. Now, the only time you don't substitute back is where maybe we have some sort of integration with limits and we change the limits as well. But here we're going to be looking at differential equations. So this question says that we want to show that this substitution, y equals xz, transforms this differential equation into this one. So before we dive in and start just doing substitution, let's see what's actually happened. If I look at this and compare it with this, there's no y terms in this. So what's happened to get from here to here, we've eliminated y. So that's what we need to do, is to eliminate y. Now, how can we eliminate y? Well, we can use the substitution. So if I see y in my equation, the differential equation that's been given, I can replace it with xz. Okay, so that will deal with this and this, but this is also like a y term, so I need to get rid of or substitute so that dy dx goes as well. So I also need to substitute dy dx. Now at the moment I don't know what that is, but I can work it out because I can differentiate this with respect to x. So that's going to be our first step. Okay, so since y equals xz, then dy dx will equal, so we will use the product rule to differentiate this. This part is like u, this part is like the v part, so we always have u v dash. We'll do that first, so that'll be x, and then the v dash, if you differentiate this z with respect to x, it becomes dz dx. So think of it like I have just differentiated a z term as if it were an x. Yeah, so that's what that becomes when you differentiate this with respect to x. Then the second part of the product rule is going to be this part times by the x differentiated with respect to x, which just becomes 1. So 1z or just z. Right, so what does that tell me? That tells me that wherever I see dy dx, I'm going to change it to x dz dx plus z. So these are going to be my substitutions. So these are the things I'm going to use to transform the or this differential equation into this one. So let's now do the substitutions. The rest is just doing substitutions now. So if I start with the dy dx, I replace that with x dz dx plus z. Then on the other side, wherever I have y, I'm going to replace it with xz. So that'll be x squared plus, now it says 3y squared, so that'll be 3xz all squared, so that's x squared z squared, all over 2xy, and again we replace that with xz, so it will become x squared z. So I'm timesing 2x by xz. So that's my first step. Now if I have a look, I can divide all of these terms by x squared, like this, so that will become 1. So what I will have is x dz dx, and I'm also going to move the z to the other side as well, so I'll take away z from both sides, so I'll have 1 plus 3z squared over 2z, take away z. Now I want to incorporate this z into this fraction, because if I look at what I've got here, so this z, that can be written, if I want a denominator of 2z, so that I can put it together with this fraction here, I can write this as 2z squared over 2z. That's equal to z or equivalent to z. So then what I'll have is x dz dx equals, and I'll have 1 plus 3z squared minus 2z squared over 2z. So there's the z incorporated into this. Now I think we've pretty much finished, and we have the expression that they're asked for, or the equation that they've asked for, because if we do 3x squared minus 2x squared, that's just x squared. So I have 1 plus z squared over 2z, so I've got that expression as required. So part A is done. Then part B says, hence find a general solution to the original equation given y squared in terms of x. Anytime you see hence, it means use what you've just done. If it says hence or otherwise, it means, well, you know, if there's a different method, use it. But hence, you look at what you've just done and use that to help you. So in part B, what are we going to do? Well, we are going to actually find a general solution for this. When we found a general solution for this, we'll substitute back, and then that will give us a general solution to the original equation here. Now this can be solved by the separation of variables. Okay, so by separation of variables. So that means putting all the x terms on one side, all these z terms on the other side. So doing that, that will give us 2z over 1 plus z squared dz equals 1 over x dx. So using separation of variables, which we've done, we can now integrate both sides, and this is a fairly straightforward integration because if I integrate this, because the top is exactly the bottom differentiated, so if that's like f of x here, I've got f dash of x, so it becomes log of f of x, log of the bottom without any adjustment. So I'll actually have the natural log of 1 plus z squared equals, now I get exactly the same on the other side, well that's just going to become log x, so log x plus c. Now I could make my substitution back and simplify, but in my own personal opinion, I think it's easier to simplify this first, then substitute back. So that's what we're going to do. We're going to simplify this as much as possible. Now we can put the log terms both on the same side, like this, minus log z equals c. When they're both on the same side, we can write this as the log of 1 plus z squared divided by z. So we'll do that. So now we have the natural log of 1 plus z squared over, now I've just realised that should be x there, not z, over x, like this, equals c. On something like this, we would do e to both sides, like this. So if I do e to both sides, I'll have 1 plus z squared over x equals, now this constant c, when I do e to a constant, it's going to become another constant. So I'm going to call this constant a. I'll just put a note here that actually a equals e to the c. So I've just replaced it just to simplify a bit. I could leave it as e to the c, but that's just a constant. So let's use the letter a. So you might write in your working, let a equal e to the c. So I've simplified this as much as I can now. What I will do is now make the substitution using my y equals xz. Now, if I have a look, my final answer needs to be in terms of y squared and x. So I need to eliminate z. So using the substitution that I was given right at the very start, which is this one here, I can write z equals y over x. So I will use that to get rid of any z's. So here, replace that with y over x all squared. I think that's the only one. So I'll have 1 plus y over x all squared, which would be y squared over x squared over x equals a. Now I need to give it as y squared equals something, so we'll multiply both sides by x, then take away y 1 from both sides, so I'll have y squared over x squared equals ax, my constant times by x, minus 1. And then I can finish it off by multiplying both sides by x squared, so I'll have y squared equals x squared times by ax minus 1. So there we go. That would be our general solution to that differential equation using the transformation. So in this question here, use the substitution z equals y to the minus 1. I suppose we could write that instead as z equals 1 over y. And that also tells us that y equals 1 over z, so I'll just keep those there just in case I need them. I'll definitely need this one, may or may not need this one, to transform the differential equation, this differential equation here, into a differential equation with z and x. So if it's just z and x, that means that I need to eliminate y. I need to get rid of y. Okay, so we need to eliminate this dy dx and change it, and also these y's as well. Okay, so let's just highlight the things that we want to remove. So these here. So first of all, dy dx. Well, if I differentiate this, I can get dy dx. So let's do that first. So we can say that since y equals 1 over z, then dy dx is going to be, now if we differentiate 1 over z, that's like z to the power negative 1, that will become minus z to the minus 2. And what have we just done? We've differentiated a z as if it were an x. Suppose we could write that instead as dy dx equals negative 1 over z squared dz dx. So now we'll make our substitution into this differential equation. So this bit here, dy dx, will replace with this, minus 1 over z squared dz dx equals, plus x times y. So we're now going to make that x times by 1 over z, we'll replace y with 1 over z. So that will be x over z equals x times y squared. So that will be x times by 1 over z squared if we square that. So that will be x over z squared. Now we could leave it like this. It's a differential equation in terms of x and z, but I'm going to tidy it up a bit. I'm going to multiply everything by negative z squared just to get rid of these fractions here. So times everything by negative z squared, we will have dz dx plus or minus, xz, if you times that by negative x squared, equals minus x. So this will be our differential equation in terms of x and z. Part B now asks us to solve the new equation using an integrating factor. So we're told specifically to use an integrating factor. Now this actually could be solved, this differential equation here, by separation of variables. We'll get the same answer, but we're specifically told to use this. Now the integrating factor, remember, is where we have a differential equation in this form, like this, and then what we do is we'd multiply every term by e to the power of the integral of p to the x dx. Now since this is not x and y, it's z and x, I'm just going to write down what it looks like in terms of z and x. So it'll be dz dx equals, basically every time you see a z you put y, you put an x, z there. So in terms of this specific question, it's going to look like this. Yeah, so we want to get it into that format so we can see what p of x is. So we'll do that first. Not sure why I put another equal sign there. That should be plus, like that. Right, so rearranging it, well actually we don't need to rearrange it, do we? It's in the correct format, so I can see that my P of x is minus x, and Q of x is also minus x as well. So the integrating factor, I'll just do IF, is equal to e to the integral of minus x dx. That is, if we integrate minus x, that will be minus x squared over 2. So there's my integrating factor. So I'm going to multiply all the terms by that integrating factor. So I'll get e to the minus x squared over 2 dz dx minus e to the minus x squared over 2 x z equals minus e to the minus x squared over 2 x. Now remember, when we use the integrating factor, this side here is the result of differentiating something using the product rule. Okay, so what did we differentiate to get this expression over here? And it's always going to be this part here is the u part, the thing that's next to the dy dx or dz dx. So this is what would have been the u part of the product, and this part here is always the v part of the product, the bit that's next to the x term. So if we continue, the left hand side is what we got after differentiating this product with respect to x, which is z times by e to the minus x squared over 2. And then we have the right hand side here. Then remember, the next step in using the integrating factor is now that we integrate both sides like this. Right, so what we're going to look at now is how we can integrate this, because you might be looking at that and think, oh, integration by parts, but there is a quicker way, there is a pattern. Now I'll just write some notes over here and see what pattern we can use. It's actually a reverse chain rule. Now to explain this, just a reminder, a quick way of differentiating e to a function is to say, right, that dy dx is that function differentiated times by e to the f of x. Okay, so that's how we would differentiate. Now that also means if we use it the other way around, so that's differentiating, if I see this pattern, f dash of x times by e to the f of x, I know that when I integrate, I should get this, obviously with a plus c on the end. So we can use this pattern in reverse. So if I see this type of pattern here, I know it came from differentiating e to the f of x. Now this is what I've got here. Yeah, so let me write down some notes to show you what I mean. So if I had y equals e to the minus x squared over 2, and I differentiated it, then my f of x is this part. So if I differentiate that, well, it's like minus 2x over 2. It just becomes minus x times by e to the f of x. So that means if I see this pattern here, it means when I integrate it, I'll get back to that. And this is exactly what we're doing here. So I know that when this is integrated, it will become this. And that's the quick way to actually find what this is integrated. So we don't need to go use integration by parts, that will be much longer. Look for this pattern. If you see this type of pattern, then we can actually use it backwards, and the same applies for things like sine x, cos x, different functions here. It doesn't have to be e to the x, but we're just using this pattern in reverse. It gives us a quick way of integrating this. So if we now go back to this, so the left hand side, the integration sign and the d dx will cancel out. That will just leave us with z e to the minus x squared over 2 equals, and then we know that this integrated is going to give us e to the minus x squared over 2 plus c. Then the last step now will just be to divide everything by the integrating factor. So divide everything by e to the minus x squared over 2, and that will leave us with z equals 1 plus our constant over e to the minus x squared over 2. And that we could call that another constant, but we might keep it like that because we're probably going to need to substitute back in the last part of the question. So we'll just leave it like that for the moment. Okay, that's a perfectly acceptable answer. So if we now look at part C says find a general solution to the original equation in terms of y and x, which means we now substitute back. Right, so if you go back to the very beginning here, z equals the reciprocal of y, or y equals the reciprocal of z. So that means that y equals the reciprocal of this. Yeah, I suppose we could replace this and put 1 over y equals that. Actually, we will do that. I think so. I'll do 1 over y equals 1 plus. Now, since this is a negative power, I don't need to write at the bottom. I can bring it to the top and write it as a positive power. So that'll be my constant times by e to the positive x squared over 2. So if that's what 1 over y is going to be the reciprocal of that. So 1 over 1 plus my constant times by e to the x squared over 2. Now notice I didn't actually change this to another constant here, constant times this, because this isn't going to be constant because I've got a variable in there, x squared. So this whole thing here isn't a constant. So I need to leave my constant like that, and that's why I did the same here. Yeah, so final answer for this would be y equals this expression that we've just written down here. So we'll just highlight that. So on this question here, it says use this substitution, u equals y minus x to transform this differential equation into a differential equation in terms of u and x. Now that means we need to eliminate y. So that means the y's need to be changed. So these y's here need to go, and these dy dx's need to go. So we can take the substitution we've been given. Now that can be easily rearranged to say that y equals u plus x, and we also need dy dx, don't we? So we'll differentiate u plus x with respect to x. So when we differentiate u with respect to x, that basically becomes 1, but we've just differentiated a u as if it were an x, so it's basically 1 du dx. And then if we differentiate the x with respect to x, it just becomes 1. So these are what I can use for my substitution. The y, I can substitute, any y's I'll substitute for u plus x. Any dy dx's I'll substitute for du dx plus 1. So let's do that. So let's start with the dy dx, so that becomes du dx plus 1 equals, now y will change to u plus x, so I have u plus x, then minus x plus 2 over, there's a y at the bottom, so that's also u plus x, minus x plus 3. Now we can simplify that, so I'll write du dx, and I'm also going to move the 1 over as well. So this equals, now the top up here, so I've got x minus x, that cancels out. So this just leaves me with u plus 2 at the top. And the bottom here, these x's cancel out, leaving me with u plus 3. So I will have u plus 2 over u plus 3, and then minus 1. Now I want to put these together. 1 is the same as u plus 3 over u plus 3. I want the same denominator, so I can put those together. That will give me next du dx equals u plus 2, so that was there already, plus u plus 3 over u plus 3. So I've written the 1 as u plus 3 over u plus 3 and put it together with the other fraction, or the fraction that's there. Sorry, I should have written minus here, not plus. Let's now simplify that. So du dx, right, let's see what we got at the top. U minus u, well that's nothing. And then 2 minus 3, that's minus 1. Over u plus 3, that's just nice and neat. So there we go. We've transformed it into a differential equation just involving u and x as they wanted. So that's part A done. Then in part B, it says by first solving this new equation, okay, so we'll solve this first, show that the general solution to the original equation, that means substituting back, may be written in this form here where c is an arbitrary constant. Right, so let's solve this. We can solve this by separation of variables. So if we do that, we will have multiply both sides by u plus 3, so I'll have u plus 3 du, and multiply both sides by dx, I'll have negative 1 dx. Now I can then integrate both sides like this. So if I integrate the left hand side with respect to x, that's nice and easy. That will be u squared over 2, or half u squared, plus 3u equals, now the negative 1 integrated with respect to x, and I've just noticed here, not sure why I've put dx over dx, that should just be dx, so let me correct that up, just in case you were a bit confused about what was going on. Negative 1, that'll just become negative x plus c. Okay, now the form they want it written in has y, so we need to then substitute back and replace the u's with y's. Now u, or y's and x's, u is y minus x. So if I now substitute back, I will have, instead of u, I'll have y minus x all squared over 2 plus 3u, or 3 times y minus x, equals minus x plus c. Now I have no fractions in this form here, so I'm going to multiply everything by 2. So I'll have y minus x all squared. I'll just put times 2 here. And then plus 6 y minus x equals minus 2x plus 2c. And I think we're almost there. So if I now move the minus 2x and 2c across, y minus x all squared, then I'll expand the bracket, so 6y minus 6x, and then move the 2x across, so plus 2x and then minus 2c equals 0. I don't need to expand the brackets because I'm looking at what they want. That's there. then plus 6y, then the minus 6x plus 2x is going to be minus 4x plus 2c equals 0. So we've got it in that form as required. Let's just highlight that, even though it's really the working that's the most important part. You should now be able to do exercise 9a on pages 182 to 183. Just a quick recap here. So this is helping us solve differential equations. Solve differential equations by substitution. And we'll just do a couple of examples. So let's say, for example, our substitution was y equals xw. Then from this you can find dy dx. So we use the product rule. Here's my u, here's my v. So u equals x, then du dx is 1. If my v equals w, then my dv dx, or v dash, it would be dw dx, because we're differentiating that variable w with respect to x. That can just go straight in. So we have u times by dv dx, which should be, or v dash, which would be this, plus the other part of the product is what we get by multiplying these two together, so that'd be plus w. Here's another example of maybe a substitution that we might have. Let's say we had y equals z squared z cubed w squared. How do we do something like that? Well, this works in the same way. So here we would have u equals z cubed, v equals w squared. So let's write it as u dash. Now if we differentiate that, that becomes 2z squared, but we've just differentiated a z as if it were an x. And v dash, if we differentiate this with respect to x, so 2w, differentiate as if it was an x, but we've just differentiated a w as if it were an x. We've pretended it was an x term. So this is the implicit differentiation. So then dy dx, that will be u times by v dash. It's going to look a bit more complicated than the last one, but the same rules apply. So this will be z cubed times by 2w dw dx, plus then these two multiply together, and we could write that as w squared plus 2z squared dz dw. So it looks a bit more complicated, but the same rules apply, and we could just tidy this up a bit and write it like this. Yeah, so you can differentiate any variables with respect to any other variable as long as you use the correct d letter at the end to indicate what you are differentiating that variable with respect to.